Hello Year 12s and welcome to our second video on electricity. In this video we'll cover some key quantities we need to know once we're talking electricity, and then we'll be looking at a few types of electric circuits, so we'll have to be able to use these quantities and do some little calculations with them. When we were looking at electric fields, we were looking at charge, because it's charges that are flowing. Remember those electrons. The quantity is charge. The symbol for charge in an equation is a letter Q. Now I put two here, a capital and a lowercase q. Usually when we're talking as charges flowing in a circuit, we use a capital letter. The lowercase letter is often used when we're talking charged particles that are moving within an electric field. So a small charged particle gets a lowercase q, charge is moving, capital Q. The unit for charge is Coulomb. The symbol for the unit is a capital C. Now once these charges are flowing in a circuit, we have a current. Current describes the flow of charges, the rate at which charges are flowing. Never ever use the term speed here, okay? It's the rate. How much charge is flowing per unit of time? Charge is in Coulomb, time is in seconds. So 1 amp, 1 ampere, symbol for it is a capital A, is 1 Coulomb per second. And if you have to write an equation, the symbol to use for current is a capital I. Easier with voltage. Voltage, the quantity symbol is V, it's measured in volts, and the symbol for that is still a capital V. So that's nice and easy here. Voltage tells us how much energy there is behind the flowing charges that are going through that circuit. So it's the work done per unit of charge, so it's joules per Coulomb. So these units, these quantities are all linked with each other. If I've got 1 volt potential difference, voltage, then each Coulomb worth of charge will convert 1 joule worth of energy. As this 1 Coulomb crosses the potential difference of 1 volt, it will release a joule worth of energy or it will gain joule worth of energy in the case of a battery, for example. Next one is resistance. Resistance, the quantity has a symbol R. The unit is ohms, and now we're running out of normal letters, so we're using Greek letters here. This is a capital letter omega out of the Greek alphabet. If you have a resistance describes the opposition to the flow of current. The greater your resistance, the harder it is for a current to flow. How many volts do I need to get, let's say, 1 amp of current? It's the relationship between voltage and current that's expressed as resistance. If you have a large resistance, you need to apply a larger voltage to get a given current. So it's volts per amp. Resistance tells us how hard it is for a current to flow. And power, you know that from physics, power is the rate at which energy is converted. Power symbol is P, it's measured in watts, symbol for that is capital W. And power is defined as rate of energy, so it's kind of joules per second over here. Okay, I could actually write that here as well, joules per second. So it's a combination of joules per Coulomb and Coulomb per second. If I multiply one by the other, I get joules per Coulomb times Coulomb per second, which is joules per second. This is where that voltage times current comes from, the voltage times amps. So the product of current and voltage tells us how much energy is converted. The current tells us how many charges are flowing per second. The voltage tells us how much energy each unit of charge gains. So it makes sense that the product of the two tells us how much energy is converted per unit of time. Now you might want to replay this part of the video 2-3 times just to make sure that the whole thing makes sense. Okay, so here we've got a very, very simple circuit. There's a paragraph or a chapter in your book that describes circuit symbols. I'm not going to talk through those. There's nothing difficult to understand. You just need to learn a few things here. You need to know that this is a symbol for a cell, a single cell battery. You need to know that that's a resistor. You need to know that's an ammeter and a voltmeter. Things like that, you'll have to just pick up from your textbook. Now, if this is a single cell, cells, power sources, have a positive and a negative terminal. The shorter, thicker line is always your negative terminal. The thinner, longer line is your positive terminal. Now, electric current is said to move from plus to minus. Now, a few of you should be wondering now, hey, wait. We've talked about current being electrons moving, and electrons shouldn't be attracted to a negative terminal, but a positive terminal. And you would be right. Electrons in this circuit will actually flow in the opposite direction of the current. That's unfortunately a historic thing. The concept of current was established or invented before we actually knew what was moving through a circuit. At the time they decided that current is moving from plus to minus. And we're sticking with this still today. And in physics books you will find your current moving from plus to minus. In reality, we know that the electrons are actually flowing the opposite way. So the current will flow from plus to minus, and in this case here will move through a resistor R. That resistor could be just that, a little resistor, which is a device that will limit the amount of current, but light bulbs, motors, your phone, they would all be considered resistors as well. And you can measure the current through it by putting an ammeter into the pathway of this flowing current. If you want to know how much voltage there is across a device or a component in a circuit, you have to attach a voltmeter in parallel around that component, because you want to measure the potential difference from before to after that component. So there's our link between current, voltage and resistance. If I have a current flowing, there'll be a voltage across any resistor, and work can be done, energy can be released in those devices, in this resistor. This resistor would heat up, for example, here. And it's really important that you remember that current is what we talk about conventional current, not the actual real movement of charges. So this first type of circuit you need to be familiar with is a series circuit. Now a series circuit has resistors connected one after the other. So we've got a power supply that produces a supply voltage. That little s stands for supply. And I've got now resistor 1, resistor 2, resistor 3. There could be 20 if you wanted to, or 100 if you think Christmas lights. But we get back to that. That's very unlikely. As many resistors as you want, one following the next. Okay? So what do we know about the current here? Current has to travel from, conventional current is traveling from plus to minus. So it has to go this way, that way. It only has one pathway. There is no other way for electrons to move than to travel through all three resistors to get to the positive terminal of the battery. Therefore, the conventional current has to be the same throughout the circuit. So I know that my circuit or my supply current that comes from the battery equals the current through resistor 1 equals the current that goes through resistor 2 and equals the current that goes through resistor 3, because it has to be the same everywhere. What about the voltage? We have a supply voltage. Let's say, shall we give it a value? Okay, let's make that 12 volts. So the voltage from the positive to the negative terminal drops by 12 volts. I've got 3 resistors within that circuit. So I will have 3 steps. The voltage drops as it crosses the resistor. But combined by the 3, it can't drop more than the supply voltage. Actually, it will have to, in this case, exactly drop by 12 volts. So the voltage will simply be split up, divided by these 3 resistors. So my supply voltage equals voltage 1 plus voltage 2 plus voltage 3. Okay? If you think of an electric circuit, if you compare it, for example, with a river. So the Waiau River between Lake Tianau and Lake Manapuri has a 20-meter drop. If I can put 3 dams in there, so a resistor would be a dam with a turbine, from Tianau to Manapuri I'll drop 20 meters. I could have just 1 dam that can drop 20 meters. I can have 2 dams, 1.8, 1.12, 1.6, 1.14, whatever, has to add up to 20. If I have 3, the 3 height differences have to add up to 20, not more, not less. Same here with voltages. I start off at plus 12, I end up at, let's say, 0. So these 3 voltages have to add up to the supply voltage. Now, what about resistance? If I put a resistor in a circuit and it has a given, let's say, 5 ohm resistance, okay, if I add then another one of the same, I think it's fairly obvious that those resistors add up. Okay, the resistance, every time I'm adding another resistor in series, I'm adding another obstacle for the current to flow through. And because all the current has to flow through all the resistors, resistance adds up. So, resistance of the circuit as a whole, the C stands for circuit, equals resistor 1 plus resistance 2 plus resistance 3, and so on if you add more. I hope this makes sense. Next, we look at parallel circuits. So this time my resistors are arranged in a way that each one of them is actually connected to the power source. That means our conventional current now has options. It can travel from plus to minus going through resistor 1 or resistor 2 or resistor 3. Now, just like your average student, current is lazy and it will take the easiest pathway possible. So if resistor 1 would have the lowest resistance, most of the current will actually travel through here and less through the higher resistances. But I think it's fairly obvious that my supply current is made up of current 1 plus current 2 plus current 3. So the currents through the different pathways add up to the supply current. Or in other words, the supply current is split up into the different pathways of this parallel circuit. If I add another resistor in parallel here, I would draw even more current from this power supply which would mean if it's a battery, I would drain the battery faster. The voltage, my supply voltage, what happens here? My resistor 1 is directly connected to the supply voltage. So is resistor 2. You can get from plus to minus going through only one resistor. So every resistor in a parallel circuit is on the same voltage, and that means in this case they're all attached to the supply voltage. So in other words, voltage 1 equals voltage 2 equals voltage 3 equals the supply voltage. They're all connected to the full supply voltage. Now comes an interesting one. What about the resistance of the circuit as a whole? So if I only have one resistor, R1, the circuit resistance would be resistor 1. However, by the time I add another resistor in parallel, I'm now giving my current a second pathway. That means there's more current flowing. That means there's less resistance to the flow of current overall. So my circuit current actually has to decrease. And if I add a third resistor, it'll drop even more. So there's actually an inverse relationship between resistances. So the equation looks like that. 1 over circuit resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. If you're calculating resistances, make sure that your calculated resistance of the parallel circuit you're dealing with, it has to be lower than the smallest resistor that's attached here. So if this would, for example, be a 2 ohm resistor, a 4 ohm resistor, and a 10 ohm resistor, I know that the resistance will be less than 2 ohm, because I've got 2 ohm just along with that. And if I add a 4, I'll reduce it. And if I add another 10, I'll still reduce it by a little bit more. There won't be much current going through the 10 ohm resistor in comparison to the 5, only a fifth, but there's still another pathway, there's still more current flowing, drained from the battery, therefore the circuit resistance will have dropped a little bit further. So those are the rules behind series and non-parallel circuits. You will be very happy to see that the equations you will have to use to work out voltages, currents, resistance and power are very, very simple ones. The first one is called Ohm's law, after the person who managed to come up with it. And that simply states that voltage is the product of current and resistance. So V equals I times R. So it gives us a relationship between current and voltage relative to resistance. The second one is that power equals current times voltage. Now you will have found within the units and the stuff I added to the little table at the start of this video, you will have found those two equations actually already. Sometimes you find a combination of these, the two. If I take P equals I times V and then take the expression of V as I times R, then I can simplify that to I squared R. So I can work out the power if I only have current and resistance known without having to work out the voltage first. You can work out the voltage first and then put it in, but yeah, so you might find some other variations of those two equations as well. So let's try and solve some problems using those two equations. Here's a small circuit. I've got a supply voltage of 12 volts, that could be a car battery, and I've got two light bulbs in parallel. Light bulbs are just another version of a resistor. Okay, they resist the current, so you could describe them as R1 and R2, like we've done before. One light bulb draws 2 amps from that power source, the other one only 1 amp. So, can we work out what is the resistance of R1, what is the resistance of R2, and what is the resistance of the circuit as a whole. Resistance, let's use this equation here, resolve it for R. R equals, current is multiplied, get it over by dividing, V over I. So I can use this down here. Voltage, both bulbs are connected to the full supply voltage because they're in parallel here. 12 volts divided by 2 amps equals 6 ohms. Resistor 2, 12 volts divided by 1 amp equals 12 ohms. What about the circuit resistance? Carefully look at that circuit. The supply current that's provided by the battery is split up. Some of it will go through the first light bulb, some will go through the second. So how much is coming out of the battery? Look at the, what we've established for parallel circuits. It's the sum out of those two, therefore it'll have to be 3 amps. Now, if I want to work out the resistance of the circuit, I can use the supply current and the supply voltage to work it out. Therefore, it's 12 volts divided by 3 amps, and that equals 4 ohms. I told you the circuit voltage, the resistance has to be smaller than the smallest single resistor, which was 6. Works perfectly fine. You could have used the resistance equation I've given you with a parallel circuit, which is 1 over RC equals 1 over R1 plus 1 over R2 as well. Have a look at that. 1 over R1 is 1 over 6 ohms plus 1 over 12 ohms. That is my 1 over RC. 1/6 is 2/12, so 2/12 plus 1/12 is 3/12 inverted, that's 12 over 3, that's 4. So my RC is 4 ohms from this equation as well. If you type it in, type 1 over 6 plus 1 over 12 equals, and then you have your inverse button, and then you get the 4. Another question you might get here in an exam paper: which one of those two bulbs is the more powerful one? And calculate the power of that light bulb. Power equals voltage times current. The voltage for both of those light bulbs is 12 volts, but the current for R1 is twice as large. So this light bulb 1 has definitely got the larger power rating. Its power is 12 volts times 2 amps equals 24 volts. That will be the more powerful one of the two. P2 would be 12 volts times 1 amp equals 12 watt. The power of the circuit, how much energy is converted by the circuit as a whole, 24 watts, 24 joule per second given off by this bulb, 12 by this. So the supply power, or the circuit power, equals power 1 plus power 2 equals 24 watts plus 12 watts equals 36 watts. I really hope that made sense. There's going to be quite a few questions in the book that make you use these equations to work out voltages, currents, resistance in series and parallel. You have to use the equations we derived for series and parallel circuits. There's a paragraph in there about voltage dividers. I don't think I need to talk through those separately here, because they are just another way. They are described, or they can be described as series and parallel circuits as well. Okay, you're just splitting up one resistor into two that are in series, and they just split up the voltage in shears according to resistance. I think if you work through those questions, they will start making sense. If they don't, you will come back to me at some stage later in the week when we have a Google Meet, and we can talk through anything that's still unclear at that stage. Until then, go through this video a couple of times, try and solve some of those problems, and see how you go. Until then, bye.